Okay, let's get started. All right, today on the screen, we have a gift from the original RLHF paper. So this is like back in 2017, paper by Paul Cristiano, which like was one of the first things they talked about RLHF, not for language models, but for little robotic creatures and making them do things like backflips when you like found it hard to specify the reward. So it's hard to specify the reward, but it's easy to know which thing is closer to a backflip or not. Like, so that's the original paper. You can go read it. It's not that different than language models. Okay, so where were we? We went through policy gradient. We still have a little bit more on policy gradient, and then we'll go to dynamic program. Maybe just a pulse check. Are we going too fast? Too slow? Like how we feel about the pace of this class, right? So maybe like too fast, raise your hand. It's okay to say too fast. Too fast, okay. Too slow? Abhishek is perfect. Nice. Rashi, close the door. Okay. So I'll do a little recap, and there are a bunch of good questions that came up in the last class, and so I went and did a bunch of research on them, and so we have some clarifications that'll make our life easier. So thank you all for asking great questions. But let's start with the recap, right? So our goal is to maximize the expected sum of rewards. We're going to do that through gradient descent, right? And so we said we're going to derive the policy gradient. It looks something like this, right? So we use the reinforced strip to get the policy gradient. It looks like trial and error, increase the likelihood of good things, decrease the likelihood of bad. And so you can approximate this expectation with samples. So you just draw a bunch of samples. This algorithm is on policy, so you only use the latest batch of samples. Okay, so that is the basic policy gradient algorithm. The challenge with policy gradient as currently constructed is that it's quite high variance, right? And so we said that it's high variance and it's sensitive to parameterization. And so we introduced this idea of natural gradient. And so natural gradient says that you can think of gradient descent as steepest descent under the Euclidean norm. And instead of the Euclidean norm, let's change it to the KL divergence, right? And you take the second order approximation of the KL divergence, and it gives you this thing called the Fisher information matrix, right? And the Fisher information matrix is the outer product of grad log pi transpose taken with the expectation over your current policy, right? So you sample from your current policy, you compute grad log pi transpose, you multiply to an outer product, and if you have n dimensional parameters, your Fisher information matrix is n by n. Right? And so your natural gradient update is basically you precondition your gradient with an F inverse, right? And here F is an n by n matrix. So if you have a billion parameter, it's a billion by billion parameter inverse. And so it'll make things better because it's not sensitive to parameterization and takes things in the trust region in terms of the function. But you have to invert this like million by million or billion by billion matrix. Okay, so to make that easier, we introduced this algorithm called TRPO. Right, TRPO had three major contributions. The first was it avoided explicit matrix inversion to this thing called conjugate gradient, right? The second is that it chose the step size carefully. So it did backtracking line search to choose a step size that leads to improvement. And because you didn't want to keep sampling, you introduced a surrogate objective. And the surrogate objective is through importance sampling. So you can take your old samples and evaluate your objective with new policies, right? And so those are the three fixes in TRPO. Yeah. Okay, and then we said, if you're going to use TRPO, the advantage estimator you have, which is a Monte Carlo estimator, the first thing, yeah.
Why is it called TRPO?
It's called trust region policy optimization, and the trust region is basically just that, like that constraint.
Oh.
And so it's like enforcing a trust region on the policy. That's it. Okay, so then we have this idea of generalized advantage estimators, which says that so far we've discussed the Monte Carlo estimator, which says take R1 plus gamma R2 plus gamma square R3 till gamma to the n minus 1 Rn, subtract the value function. So that's just the Monte Carlo estimate. But we said that that's high variance, whereas you can do the one-step bootstrapped update where you say you're going to replace everything which is later on in the update. So like all of this stuff you can replace with gamma VS2, right? And so the idea of bootstrapping is to say that you're going to replace sum of things in the future with a function approximated value, which is V, right? And so the one-step bootstrap update is R1 plus gamma VS2 minus VS1. And you can think of this as like you're eating up more and more and more of the sum with the value function, right? And so the one step is you eat up everything in the sum except for the first step. And the fully Monte Carlo is you have no value function. You just have a sum of values, sum of rewards, right? And so the argument here is that this is low bias, high variance, and this is high bias, low variance. And the argument here, which we'll get into a little more, is that when I have function approximation, I'm going to lower the variance because I can share things across different data sources. But if the V is wrong, it's going to be a biased estimate, right? And what GAE does is it says that if I have a bunch of these estimators, I'm not just going to take any one of them. I'm going to take a geometric sum of all of them, right? With a parameter lambda. And so that's the general. So we're going to do the same TRPO update that we're going to have anyways. You're just going to like substitute, instead of this advantage you compute on policy with just samples, Monte Carlo, you're going to substitute with this like averaged thing across many different estimators. Yep. So just a plug-in into TRPO. Okay. And then the last thing we said is, hey, this TRPO stuff is too complicated. And so we're just going to get the vibes of TRPO with this algorithm called PPO, right? And PPO, our proximal policy optimization is just like going to clip the ratio between pi theta and pi theta I, which is your current iterate, and just going to say, don't let the policy move too much. And so you're going to clip it between 1 minus epsilon and 1 plus epsilon. Right, so the nice thing about it is you could take multiple mini batch gradient steps. You don't have to do any Hessian inversion, no conjugate gradient, just use Adam, right? And it's like nice and stable, which allows it to scale to really big models. So a lot of your language models are training with something that looks PPO-like, right? So that's a recap. Any questions, things that came up in the last 2 days that we should talk about? Yeah.
You say that they're PPO, like what else is there going on?
So one of the things we talk about is GRPO, which is like a particular way of doing PPO without having a critic at all. And so they avoid the critic. So they avoid like ever subtracting the V functions. We'll talk about that in the next one. And then there's like some regularizations. They do like you regularize to a base policy, you add some entropy, you add some like soft. But it's just PPO. So the complaint that a lot of people have with language model RL or RLHF with PPO is that it's like not, the dynamics of the world are kind of stupid. In the sense the dynamics of the world are just concatenating like sentences, right, or words. Whereas like in like a robotic setting or something, you have like real interaction with the world. And so like I think there's like debate on whether it's RL or not, but I think it doesn't matter. We just end up using PPO. Okay, so to get at the point of like what else do we have? First, we should see, does PPO work for everything? And there's a nice paper. There's actually a few papers like this which go and analyze the like details of PPO implementations, and then they find that like the good performance is yes, some because of these things we talked about, but also it like depends on lots of like other stuff. So like reward normalization, observation normalization, clipping, the initialization really matters. Like the variance initialization really matters, and they find that like different implementations for the same tasks have like huge variance in performance. And so I think there's still an open question about which things are details and which things are not. But like often things that you dismiss as details make a huge difference in performance. And so I think it's not that well understood. So I can send over a few articles on Ed, but this is a good one to read, which talks about some of the implementation details in any PPO algorithm. Okay, so if you heard of PPO, you probably heard of GRPO, right? And GRPO is like produced like last year. And I think they showed really good results on language models. And the key premise of PPO is to like replace this like critic. You don't want to, often with, especially with language models, it's kind of annoying to learn the critic. You don't always do a good job. So the idea is, can you do all the stuff in PPO, but can you do it without a critic? Right? No critic. And so the the key idea in GRPO is that in like, let's say GAE, you compute this kind of advantage estimate, R plus gamma VS prime minus VS. We want to do this without any V, right? And so specifically what they argue is that in language models, you can like for the same prompt, you can sample many completions, right? So you can kind of like teleport and sample many things. And so for the same prompt, you can sample a group of completions. And then all you want to do is instead of computing the advantage with the critic, which is really across many states, what you do is you just sample many completions from a single prompt. You score each of these with a reward. And then you like normalize the advantage by subtracting the mean of all those completions and dividing by the standard deviation. So you just whiten with the mean and standard deviation of that group of completions for a particular prompt. Right. And so you're saying that like for any prompt, I'm just going to sample a bunch of completions and I'm going to see like how much better is my particular completion than the average for the completions for that prompt. Right. And so you just compare it to a group of other comparable things. You don't need to compare it to some other state or anything. Right? And so the point is you like don't actually need function approximation if I can sample a group of things from the same prompt. Yeah.
Doesn't it mean that we have like key fonts and then be the mean of standard deviation of those?
You have for each prompt, you'll sample k completions, and you're going to take the mean and standard deviation of those k completions per prompt. So this thing is going to be computed per prompt. It's going to be different. So that's the idea behind GRPO. It's basically looking at the differences between many different choices at a single state. And it's not really trying to compute a function approximator. Like for instance, the values at different states might be super different, but like who cares? Like the argument is basically I only care about other completions at the same state. Right? So I don't care about like if I had this prompt and I had another prompt, right? I don't care about these values. I only care about the relative comparison of things at the same prompt, right? Or in robotics, I don't care if like that state matters or not. I really care about at this state, which of my completions really matter. And so, like the other thing that's used, the reason you can do this also in language models is like you don't have the same long-term dependencies, right? In the sense you can like sample an entire trajectory, and you can like score the whole trajectory. And so here what you do is you sample a prompt, you complete the whole prompt, and then you take the mean and standard deviation of rewards for the whole prompt. So it's stupidly simple, but that's kind of what helps lead to a lot of the reasoning results that you see now. And it's just because the like critic is often unstable or it's biased and it's hard to learn. And so they get rid of it. Yeah. So when I say reward here, it's actually like a sum of rewards. In language models, there's like, you don't really score partial completions. You score the whole completion. The sentence doesn't have meaning until you complete it. There are some examples where you have process rewards, but in these cases, you're scoring the whole thing. Yeah. Oh, this like with the reward. Yeah, you have a reward. So in all of the stuff we've assumed so far, like a reward will show up. In language models, we'll view like a reward. Like another. But they argue that it's easier to learn that than like a critic. Just like a score. Because yeah. Okay, so a few additional tricks, like as I was talking about, is entropy maximization. So a lot of times if you're running PPO and you just run it, it'll collapse, like the entropy will collapse and then you never recover because you just never sampled enough. Like your variance gets too small, it doesn't sample enough. And so you just basically add the Shannon entropy to your objective and with some like regularization term or some weighting term that helps like encourage exploration, right? So you can kind of think of it as without it, like the only exploration you have is from random noise. And if you add the entropy bonus, you're explicitly encouraging it to have weight on other actions. And so entropy maximization helps with exploration, helps with reaching higher performance, and also helps with the optimization landscape. And the second thing that is often used is like KL regularization to a base policy. So for instance, in a language model, you'll have a base policy that comes from SFT. You like supervise, fine tune a base policy, and then you try to do RL on top of it. And so what you don't want to do is you don't want to change the policy that much, right? And so you typically will try and KL regularize your pi theta to not change that much from pi theta old, right? So pi theta old in our case is like the base policy. You just add a KL regularization to the base, and that prevents the policy from shifting a lot.
So you have one completion from your policy and then I guess, other completion.
You sample K completions from your policy. So like, imagine that you were at this prompt, you sample K different completions for the same prompt. And then so you sample a batch, and then you compare things within the batch. So imagine that I had prompt 1. I sampled completion 1, 2, 3, 4, blah, blah, blah. Then I took the mean of all of these. I subtracted the mean, I divided the standard deviation. And then I took the second prompt, and I sampled a bunch of completions again. And so you sample like K completions per prompt. So that's your group.
Right. Are there instances we wouldn't be able to sample like K-fold completions from like the same sequence in the fold?
I think if your space is too big. Like basically, if you like if your completion space, like which in this case, your trajectory space.
Oh, like if it weren't efficient to sample one trajectory, yeah.
I mean, you could always do it, it just wouldn't perform well. Okay, so you do entropy regularization and KL regularization. The goal is to encourage exploration or to prevent collapse. So like, you really don't want to lose the behavior that's in your base model. You just want to sharpen it often. And there's this really nice paper that's pretty dense, but it kind of shows that adding entropy is not just like a cosmetic thing. It also makes the optimization properties of your policy gain algorithm converge. And so the argument here is basically like, it smoothens the landscape. When you add entropy, it smoothens the landscape of optimization, so it doesn't get stuck in like sharp local optima. You can think of entropy as like smooth. It's like a smoothness filter on the landscape of optima. But yeah, go read this. You might find it fun. Okay, so that is basically all we're going to cover for PPO, right? So we had some questions from last time, which I'll address. But any broader thoughts, concerns before I move to those questions? Nope. Okay, so first thing is, I think Harini asked last time, what does the Fisher information mean, right? And I think it's useful to think about Fisher information as basically a sensitivity matrix, right? So it's telling you basically how sensitive is your likelihood to particular directions in parameter space, right? And so you can kind of think of it from the perspective of like, if you take the eigenvalues of your Fisher information matrix, that gives you the most sensitive directions. So if I had to like find the most sensitive directions of parameter space, I would just do like PCA on the Fisher information matrix, right? Another way of looking at it is if you like multiply, you take a quadratic norm of some direction delta theta under F, you can think of it as like, it's looking at the dot product with grad log. So it's like the directional derivative. And so you see like, how much does changing in some delta theta affect the log probabilities? Right? And so you can kind of see that like in regions of the parameter space where like you don't have a lot of effect, this number will be small, so it'll be pretty flat. In the regions where you will have a lot of effect, it'll be pretty sharp, right? So the Fisher information matrix, you should just think of it as a sensitivity matrix to directions in the parameter space. Right? And so by multiplying by the inverse of the Fisher information matrix, you're like renormalizing it. So all the directions kind of have the same effect. Okay. Second question I think we asked last time was, is the Fisher information matrix always invertible, right? And so it's not. It's PSD. It's positive semi-definite, but it's not positive definite, right? So it can have zero, some zero eigenvalues, right? And so then it's not invertible. And so in those cases, you either use the pseudo inverse, right? So use the pseudo inverse, which is not exactly the inverse, but like is well defined, or you like do some damping. And so you can add like a lambda damping term, which is a little bit wrong, but like allows it to be invertible. And so that's typically how you'd deal with that. And then the last question, which Sid asked, was around why is this like advantage thing bias, right? And so we're constructing this one-step advantage estimate. Let's call it R plus gamma V, ST plus 1, minus V ST. It's going to be V phi. So V phi is our estimated value function, right? So this is what our estimator is going to be. Our true advantage, like the thing we don't know, right, is basically RT plus gamma V pi. So V pi is the true value function, right? Not the estimated value function, the true value function. And what we want to compute is the bias. And so the bias is the difference between the expectation under my estimator and my true advantage, right? And so this is my estimator. I'm going to take the expectation under my estimate. When something is unbiased, its expectation is the same as the true value, right? And so I'm going to show that what we want to show is that this estimator, when you take its expectation, what is its difference from the true value? That's the bias, right? The bias is going to be take my one-step estimator, take its expectation, and find its difference from the true advantage, right? So if imagine the true advantage is imagine I have the perfect value function. If I have the perfect value function, that's going to give me a pi. If I have an estimated value function, that's going to give me a hat t super 1. And I'm going to like subtract the expected estimator minus the true. Okay, so if I do some substitution here, right, you can basically take this expression and basically subtract this expression, right? So these terms cancel out, right? And you're going to have like gamma times this minus this and minus like this minus this, right? And so your bias comes out to be gamma expected v phi minus v pi minus v phi minus v pi. Yeah. So now let's denote v phi minus v pi as called an error function E, right? State dependent. What you're essentially saying is that your bias is gamma times the expected error at state st plus 1, given some state st and at, minus error at state st, right? All we did is we substituted in the expected advantage, we subtract out a pi. And so we can like write down the bias as this. And this bias, if the error is truly 0 everywhere, if the error is 0 point-wise everywhere, this value is going to be 0. It's going to be unbiased, right? So if v phi was equal to v pi, this is going to be unbiased. But if v phi is not equal to v pi, this doesn't need to be unbiased, right? And so an argument for why this thing is biased is if you literally compute the bias, unless E is point-wise 0 everywhere, it's going to be biased. Yeah. So maybe useful to just like work out if you're ever confused. If in general, across the next few things, we're going to like accept some amount of bias to reduce variance, right? So it's okay to have a little bit of bias as long as it reduces variance a lot. So just a trade-off. Cool. Any questions? Did that answer most questions that came up last time? Do we feel pretty satisfied with those responses? Yeah? No? Good? Cool. Alrighty. The next thing is like totally unnecessary, but it's my class, I can do whatever. And so here's a thing that no one uses, but I think is kind of fun. It's this idea called Kronecker factorization. And Kronecker factorization is basically, it's not trying to avoid the Fisher information matrix inversion. It is trying to make it easier to do, right? And so we're gonna like introduce a few things, but like maybe it'll be useful somewhere else in your life, but nobody uses this, just for context. So the idea here is that your Fisher information matrix is high dimensionality, it's hard to invert. And so you introduce this idea called Kronecker factorization, which is a particular factorization of your Fisher information matrix, which makes it easy to invert. It's an approximation, okay, which is going to make it easy to invert. And the way you're going to do it is you're going to start by like block diagonalizing your Fisher information matrix layer by layer. And then you're going to take each block diagonal matrix and express it as a Kronecker product between two things. We'll talk about what a Kronecker product is, but the Kronecker product allows you to do easy inversion. So you're going to do two things. You're going to start by block diagonalizing your Fisher information matrix. So imagine this was your Fisher information matrix, okay? This was like, and like imagine that these were your parameters. This was layer 1, this is layer 2, this is layer 3. Right, you're not going to consider a full matrix. You're going to consider like a block diagonal matrix. Yeah. So you're going to like ignore all the like off diagonal terms. Yeah. So you're going to block diagonalize your matrix, your Fisher information matrix. And then each of these block diagonal terms, I'm going to represent as this Kronecker product. And a Kronecker product is like a particular form that makes inversion easy. Yeah. And so we'll talk about how to do that. But that's the vibes of this next section. Yeah, we're going to block diagonalize and we're going to express as a Kronecker product. And if we do that, then inversion of this matrix will be easy. Okay, So let's start by like talking about a Kronecker product. What is a Kronecker product? So if I have two matrices, A and B, they're kind of shown over here, A and B. And let's say A was of size M by N and B was of size A by B. You can kind of think of the Kronecker product as if you took the first matrix and like slid it along the second matrix, right? And so you're like saying that like, imagine that you had like one matrix and another matrix, right? You're going to like multiply this thing by this thing and like tile the first matrix along the second matrix, right? And so the size of the matrix you're going to get is MA times NB. And so you're going to tile every element. Like you can see that every element of the first matrix is multiplied by the whole second matrix. And then you're like tiling it. And so with these two matrices, right, you will get a much bigger matrix, which is essentially the tile of this matrix times this matrix. Right? So that's what you'd call a Kronecker product. It's a little counterintuitive, but you can kind of think of it as you like sliding one matrix, you're multiplying each element of another one matrix by the second matrix and like tiling it a bunch of times. Yeah.
How is it different than I thought that's what it does too.
Yeah, it's similar. Yeah.
Okay.
Same thing. Yeah. But it's different than a matrix multiply.
Yeah.
Mhm. Yeah.
The audio, doesn't matter.
Yeah, that's right. Okay, so some nice identities about the Kronecker product is if you ever take UV transpose and vectorize it, that is the same as U Kronecker product V. If you have a product of two Kronecker products, you can take them as like you have A cross B and times C cross D, but as AC cross BD. And the most important one is if I have A cross B inverse, I can write as A inverse cross B inverse, right? And so these are like some identities about Kronecker products. But the reason the last one is useful is A cross B, remember, is like a big ass matrix, right? But A and B are not that big. And so if A and B are not that big, what this allows us to do is invert much smaller things. And if I have much smaller things, then I have to like invert smaller things, and I can take the Kronecker product of like things that are inverted, which are small. Right. So the idea is if I can express my Fisher information matrix as like a Kronecker product, then the inverse is easy to compute because I only have to invert small things. Okay, so what we're going to do is take our Fisher information matrix, right? We're going to block diagonalize it. So we're going to ignore any cross correlations between layer one and layer two. It's like obviously an approximation, right? But we're going to like only consider correlations between layer one and layer one, layer two and layer two, layer three and layer three. Yeah. And then we're going to say that each of these block diagonal terms we'll write as a Kronecker product of two things. And then you can like invert those two smaller matrices, and then like you're never inverting like a billion parameter thing. Right with me? It makes sense. It's like a jump in logic, but let me jump to it's like it makes a big difference. Like it leads to big improvements in performance. So it's not just like completely arbitrary, right? So like blue is when you have the Kronecker product approximations, when like orange and green are like TRPO, or I'm colorblind. So whatever is green, okay. That is TRPO. That's poor. So it's not a arbitrary thing, or it is arbitrary, but it's not like a useless thing to do. Okay, so going to block diagonalize, we're then going to try and express as the Kronecker product. Yeah. That's a good question. I think it just like avoids some of the numerical instability of TRPO. And so I don't think there's like a great reason because both of them are like F inverse in some sense, but there's like different approximations. So empirically this approximation.
Why do people not use this? Because of memory?
Yeah, I think it's still memory, and with larger models, I think PPO tends to scale better than Kronecker approximations. It was like a big thing in like 2017 and 18, and then like it just didn't scale as well. Okay, so what we're going to do is we're going to try and compute the gradient like of our loss function. Let's call our loss function L. It's going to be the log probability, right? We're going to try and compute the gradient of our loss function with respect to some weight matrix, call it W, right? And so let's say like our activations at some layer were A, like our post layer activations are going to be S, right? And so if you ever want to compute the gradient of your loss function with respect to W, just by using chain rule, you can write it as the gradient with respect to S times the gradient of S with respect to W, which is A transpose, right? And so you can write the gradient of L with respect to W as the gradient of L with respect to S. Basically, you can write it as this times this, right? And this is just A transpose. Yeah. And so the nice thing now is that going back to our matrix identities about the Kronecker product, like this thing over here, you can write it as essentially you can write it as A, you can write this as like A cross delta LS. Yeah. Just by using the first identity, if you have UV transpose, you can write it as U Kronecker product B. Right? And so you can write this expression, grad LW, as A Kronecker product grad SL, right? And so now if I look at my Fisher information matrix, it's going to be the gradient times the gradient transpose. So remember, it's grad log P times grad log P transpose, right? This is what we had earlier. But we just express these things as a Kronecker product, right? And so this is going to be A cross grad LS times A cross grad LS transpose. Yeah. But we're going to use the second identity for a Kronecker product. And then you can write this as basically a Kronecker product between AA transpose and grad SL transpose. Right? And so far we haven't made an approximation. It's just the matrix identities, right? So we've like started with the Fisher information. We've said that is just by the definition of your weights, you can write this as a Kronecker product between A and grad SL. And then we've just used the second Kronecker product identity to get here. And this is the big jump in logic in this approximation, is that this is like a pointwise Kronecker product, and then you take the average. And what they do, which is a little egregious, is that they like approximate it as the expectation of the first term, Kronecker product, the expectation of the second. Right, so they're saying like, rather than taking the pointwise Kronecker product and then taking the expectation, you take the expectation and then you take the Kronecker product, which is like kind of crazy. But the cool thing is that it kind of works. But I don't have a great justification for why it works. But basically by doing this, you're like ignoring some cross correlations between your activations and your gradients. But essentially the big jump here is that you are taking this Kronecker product inside the expectation, and instead you're taking the Kronecker product outside the expectation. Arbitrary jump. But what this allows us to do is now this is a covariance matrix on activations. This is a covariance matrix on gradients, right? But those are like much smaller matrices. And then I can invert both of those, right? So now I can express my Fisher information block as basically A Kronecker product S, where A is the covariance of activations and S is the covariance of gradients with respect to like post-layer activations. And now I can invert it, right? So the nice thing I know about like A cross B inverse is that it's A inverse cross B inverse. Yeah. And so now I have this small matrix. At the small matrix, I just need to invert these things. Right, so what they do here is they compute this expectation, you get two matrices, you invert these small matrices. But the big jump in the approximation is that this thing is definitely not equal to this thing. Yeah. Is it a sparse matrix? Oh. I don't have great answer, but it seems to work pretty well. But the idea here is that you like convert into a Kronecker product of these smaller matrices, and those you can invert, right? And so in terms of like computational savings, right? So imagine that you had your Fisher information matrix, which is 60 million parameters, right? And then you like take one block of that, you do block diagonalization, and you still have like 4 million parameters. And this is AlexNet. This is like way 10 years ago, right? And you still have to invert this 4 million by 4 million thing. But if you do the Kronecker product, you're only inverting like a 4,000 by 4,000. So you get like these big computational gains. And at least on these benchmark problems, it seems to do pretty well. But I think it's an open question why that approximation works that well.
Yeah, technically, we should all know about this. Just more time steps, so is that?
I think deep RL is a game of which approximation does. And so it's like, yes, in principle, everything should converge. But like when things are non-linear and a finite sample and so on, it's like not clear which ones are better. And with neural nets, it's not clear which ones are better.
Yes, TRPO is being tough shit.
Yeah, yeah. So don't use TRPO. Definitely don't use actor and use PPO. It just works the best. Okay, but I thought it was fun. It's fun as a tool to know. I think this idea of a Kronecker product and having it be invertible and so on is a fun tool to know. But I don't know if it's that useful for any of your policy gradient needs. Okay, so let's kind of wrap up policy gradient. The pros here is that it's simple and easy to implement. It's generally pretty stable. If you run PPO versus like SAC, the curves will go way up and down. It generally works well with larger and larger models and doesn't need like a lot of domain-specific assumptions. But it's like sometimes hard to debug. It's a little hard to provide any guarantees on it. And it's super, super sample inefficient. So the reason you don't use it for robots, for instance, is just that it's too sample inefficient. You use it for robots when you're doing sim to real, but you never use it on real robots directly. Right? And so in domains like language models where samples are cheap, it's okay. But let's say you're doing like multi-turn interaction with users, like unclear if PPO is the right move. Yeah.
What is the trajectory in Dota?
What is that trajectory? What's it?
In Dota, like how do you?
You just like I guess you would control some set of the players, right? So like the agent would control like 3 of the players, and you'd put them in an environment with a bunch of other players, and you would just like play the game. And so
Is one rollout just the full 30-minute game?
that's a great question. I'm guessing what they do is they actually break it up into shorter episodes. And you to break it up into shorter episodes and you episodic learning. But I actually haven't read that paper in enough details. But I'm guessing you break it up. Yeah, so you don't do a 30-minute episode. Okay, so since the grad class, I think it's useful to talk about some frontiers, right? So it's still open to see whether like policy gradient converges for the broader class of nonlinear function approximators. There's a lot of nice work on like systems and like finding ways to like parallelize and do asynchronous updates and so on for these kinds of policy gradient methods to make use of scale. There's better methods for variance reduction. Learning from images, this has gotten a lot better, but it's still much worse than learning from like low dimensional compact state. Bootstrapping from prior data. So if I had prior examples, like what's the best way to use them? Multi-agent policy gradient is there's still lots of open questions in multi-agent RL. And then lastly, I've been looking at a bit is like, how do you fine tune models like generative models like diffusion where you don't have likelihoods available? And so maybe let's touch on a few of these and why they're interesting. So I think there's like, some of you I know work on these kinds of convergence things, but generally there's like proofs in the LQR, LQG case for the convergence of the global convergence of policy gradient. Some of them from UW, but it's not that well understood in the deep learning case, either theoretically or empirically. Like even empirically, you'll find that policy gradients are often making these egregious approximations. They're like still high variance and they kind of work. And so I think empirically, those are a bunch of nice papers that analyze whether the policy gradient is truly implemented correctly and like what is the variance and like which factors matter. And so I think we don't have a great understanding of when these things work and when these things don't work empirically with large models. But yeah, open question. I think it's super interesting. The second is that to make a lot of these models work, you need to scale up to like thousands to millions of environments. And so like, how do you design systems that can take samples over them? How do you do asynchronous actor and critic updates, and how do they like talk to each other? And so there was a bunch of work a few years ago on doing this for video games and things like that, but there's still open work on how to do that for LLMs and robots and so on. So we find that it makes a huge difference if you can scale up the number of parallel environments. And so, yeah, it's good place for systems work. In terms of better variance reduction, there's been a bunch of interesting work on like action-dependent baselines. So we've talked about baselines which are only state-dependent. So if you look at this baseline, it is like, normally we said if it's B of ST, it's unbiased. But if it's B of ST comma AT, it's biased. Right? So lots of people have been thinking about like, if I had to introduce an action-dependent baseline, right? Like, how do I make it unbiased? And so these are some nice papers which talk about like alternative estimators. So like often what you'll do with an action-dependent baseline is you'll subtract out the baseline, you'll add back the baseline, and then you'll like estimate the thing you added back in a different way. You'll estimate it in like a lower way. And so there's cool work on like action-dependent baselines. There's been work on scaling up to higher dimensional observations and actions, so like humanoids and hands and things from perception, which has been non-trivial. One of the interesting problems that I find is this like student-teacher distillation setting. So imagine that you did PPO and you did PPO from state because it's way faster, right? And then you have to like use it to train something that goes from vision. Right? And so you have like a policy that works from, if you have privileged information, privileged state, but then you have to get something to work from vision, which is not privileged. So how do I actually, like, you could do supervised learning between those two things, but the solutions might not be the same. Like the solutions for privilege and solutions for not privilege might be different. And so how do you actually use the privileged policy to inform the not privileged policy? It's not that trivial. There's questions around bootstrapping from prior data or off policy data. So there's been a bunch of nice work on off policy gradients, but also like robotics methods that bootstrap from prior data and still learn efficiently. Multi-agent policy gradient is still hard, especially as you go to like millions of agents, let's say. And getting that to be stable, like the convergence properties are not the same as single agent policy gradient. And so I think the challenge is here that it's non-stationary, different agents keep changing. Data efficiency can be really hard with multiple agents, and like how do they communicate with each other? And lastly, is when you have models like diffusion models, you don't have easy to compute log likelihoods, which means you can't take grad log likelihood. And so in those cases, you have to do like all sorts of funny stuff to actually compute policy gradients. Like if you don't have grad log likelihood, like none of the things work, right? And so in those cases, you either do things like you do diffusion through like individual steps of the diffusion chain, treating each of those as actions, or you compute some surrogate to the log likelihood, which is, so the top algorithm is one called EPPO, bottom one's called FPO, but they're all like new methods in the last year. We'll try to solve this. Okay. Some people, like me and some of my collaborators, like idiots, tried to solve real robots with PPO like 10 years ago, and it totally didn't work.
2.5 hours, the agent
Or it works on these
successfully
settings,
opening
but
the
nothing
door,
more.
even in the
And
presence
so I
of
think there's
exploration
two questions
noise.
about how to use
At
the
this
ideas
point,
from
training
PPO to
is
inform
fine-tuning
real
the policy.
robot learning. But if I was to do robots with PPO, I would do sim to real. It like works super well for sim to real. So train in sim, lots and lots of samples, and then transfer to the real world. So you get like quadrupeds and hands and like lots of nice results that way. And so state of the art in like things like humanoid locomotion or dexterous manipulation is often large scale RL with PPO and simulation and transfer to the real world. So off policy RL, while great for the real world, often does worse in simulation. Okay, so generally policy gradient methods are simple. They're like the gap from the starting point of reinforced to PPO is not that big. We covered it in 2 days, right? But there's still lots of open questions. You can go from policy gradient to NPG to PRPO to PPO. But there's big sample efficiency problems and you have like high variance. So if you're trying to get policy gradient methods to work, like try to fight the variance. But lots of open questions. And so, yeah, hopefully some of your projects will be around this. Project proposals are due today, I think, right? And homework 1 should be out now. So yeah, please take a look. Cool, that's policy gradient. Any questions? We feeling good about policy gradient? Should we release homework 2 on policy gradient immediately? Okay, let's take a couple minutes and we'll get to dynamic programming now.
I sure hope. I have no idea. Yeah, I don't know.
What's up?
Okay, so for a good idea.
You're good.
You have your reward for your policy is
Yeah, I.
like rollout, right? Like which is one sequence. Like, and then you're trying to estimate the value of the state. State.
GRP or GRP?
GRP. You're trying to estimate the value of the state that you started with that you're in right now. So you do a rollouts with the same policy, right?
Yeah. Stochastic.
Right. So like in an extreme case, what happens if you just keep getting the same trajectory that you already set?
Yeah, then you're in trouble. Yeah. So, but that's true in any policy statement. Like imagine that you like whether you do GRP or not GRP, right? If I only have like one thing at any particular, if I only have one option, then I only have the only thing I can do is increase likelihood.
I see.
And so, like typically RL is like a guess and check paradigm. So it's not that if you sample one thing, it tells you where to go. It's like if I sample K things, it tells you what the best thing is. But at no point does it say like if I have one thing, I know where to go. So it's all about contrasting stuff. So if I can't contrast stuff like RL,
Right. So I guess if you had an actual critic, your actual critic would be just as screwed as.
it'll just like subtract a constant, but like it has nothing to compare to.
Uh-huh.
So there's no options to change.
And then if you, let's say like half of your K is what you originally sampled, do you filter that out or?
Half of your K is what you originally sampled. So what do you?
Like I think on the slide, there was something, it said something like only compare against other.
Other completions at the same state, right?
Yeah, yeah.
So when I say other, I don't mean like if I'm okay with repeats at the same.
Okay.
I just don't want to compare with completions at another state.
Okay.
So it's okay if you have repeats. You include them in the like you don't do anything fancy. You don't need duplicate.
Right, right.
Because you actually do want to keep their likelihood around.
Yes.
But if there's like anything at another state, you ignore all of that.
I see.
Because your value function is not function approximate across states. It's just for that.
Right, okay. All right, that makes sense.
I also saw the same.
As long as we all solve steering, it's
Yeah, I was able to see. All three.
nice. Okay. Very cool. Okay, let's keep going. The last bit we're going to cover today is on off policy RL, right? And so, as usual, I made way too many slides. But in off policy RL, we're going to start by motivating it. We're going to talk about like what you actually need to get it to work in practice, which things are issues when you apply this with high dimensional continuous spaces. We'll talk a little bit more about convergence and like why convergence in off policy RL is a little less clear. And we'll talk about separators. Okay, so we're roboticists, or I'm a roboticist. So I want to apply policy grid to robots. And so how do we make policy grid suitable for robots? Well, we want to go back to our original problem and say that what makes policy grid inefficient, right? Like the first thing that makes it inefficient is that it's on policy. Every time I need to compute this update, I need to do it on the latest batch of samples, right? But okay, we like constructed this surrogate objective, right? We like made this like surrogate objective of PRPO and on PPO. Like, why does that not just solve our problem? Like it's off policy, right? Technically, it's off policy. I'm sampling from some old thing and I'm taking many updates, right? So why is the PPO update not enough? Be off policy. My off policy, I want to use all my past data. So what gives? So let's look at it again. Let's go look at the objective. So what is our PPO objective? Here's our PPO objective, right? So okay, I guess I don't have my surrogate objective on. But the surrogate objective, if you remember, was that I'm going to sample states and actions from my old policy pi theta I. I'm going to construct pi theta over pi theta I times advantage, right? This is my surrogate objective. So it's technically it's off policy, right? I mean, important sampling. What's the why is this not always a winner?
Your weights from like your very old rollouts are just like very different.
That's right.
from what you're,
That's right.
Like gonna update to then.
Exactly. So important sampling only works when you have support overlap. If you don't have support overlap, those importance weights are gonna like freak out. Right? The second thing is that for when I constructed the surrogate objective, I made like an approximation, right? I canceled out these two things, and those things only work if pi theta and pi theta I are pretty close, right? And so you have, whether that's through clipping or through a trust region, you have to have those things be close to each other, right? And so policy gradient doesn't really work unless the things that you're off policy with respect to are like pretty close to your current things. And so we want a way to be way more off policy, not just use the like latest thing for a few steps, but be way more off policy. Right. So our goal is going to be to make off policy algorithms, which are not just using like the latest data or like a little more than that. And the second is that we have a high variance estimator, right? So remember we had a single step update, so it's still a high variance estimator. And so we're going to try and construct, in this section, we're going to construct an off policy update, which is lower variance. Right? So our goal is going to be to try and use the same ideas as policy variance, but try to reduce the variance and allow it to use off policy data. Okay. Okay, so our goal is going to be to develop a low variance off policy RL method that can bootstrap from prior data. And like learn way more efficiently. So policy gradient will take 100 hours to learn. We want to learn in like 20 minutes. Yeah. Okay, so let's look at this problem again. So we have this like single sample estimate, right? So we said that like at some state S, I only have the sum of rewards in the current trajectory, right? But what I want is something that looks more like this, right? Like just like GRPO, right? But you can't do GRPO on robots. You can't like reset to a partial state and do the same thing, right? So what you really want is something more like this. You want to compare the outcomes of different things at the same state. And so the tricky part is that I can never do that because in a measure zero state, I like never end up in the same place unless I can teleport. Right? And so while I want a lower variance estimator, it's hard to get that. And so what we're going to do, like any good deep learner, is we're going to like use the magic of function approximation. So we're going to say that, hey, I might not ever end up in the same state exactly, but I might end up in close by states, right? And what function approximations are going to allow us to do is if I train on this, I train on this, and I train on this, then I can like bundle the states together because they like have some similarities, right? And so you can think of function approximation as a way to like transfer information between this, this, and this. And by sharing that information, I'm like learning from all of these data points rather than just one of these data points, right? And so you can think of this like this next idea of like dynamic programming or approximate dynamic programming as using function approximation to like lower the variance between different states, even if I never revisit the same state exactly again. Yeah. Cool. So we're going to introduce a little bit of notation. So we're going to introduce something called a Q function. So a Q function is saying that if I start at some state ST, take the first action AT, and then follow some policy pi thereafter, right? That's going to be the expected sum of rewards in that case is going to be what you call your Q function, right? So it's kind of like, it's important that the first action is AT and not just sampled from pi, right? So the first action is fed into the Q function. So you take some action AT, and then you act according to pi, right? And you take the sum of rewards along this whole trajectory, and that's your Q function, right? And so you can always define Q. There's like lots of different Qs. You talk about your Q pi, Q star, Q hat. But we're going to define Q pi as if I started ST, took the first action AT, and then followed the policy pi theta. It's going to be the expected sum of rewards in the future. Yeah. And so you can kind of think of it as like, if you go back to the notion of what we want, right? It's saying that at the first state S, I'm going to take, let's call the state S. I'm going to take my action A, and then I'm going to like average over many possible futures that the policy could have taken, right? So I'm always going to take the first action A and then sample from the policy thereafter. That's the Q function. So you're going to take the sum over the future rewards, you're going to average them, right? So the Q function, you can kind of think of it as like a proxy for like the thing that we care about, like this thing that we care about. So in a way, you can think of the Q function kind of like something that tells you how good an action A is at some state S by measuring the expected future rewards when you act according to A, but you're following policy pi after that. And it's really important that you follow the policy pi after that. You do one step off and then you follow the policy because that's what allows you to be off policy. And so I'm emphasizing it because it matters. Okay, and we're going to argue that the Q function, when trained properly, doesn't need to have multiple actions at the same state. You can like bundle things across like nearby states because you're function approximating Q, right? You're representing Q with, in our case, Q is going to be some neural net, which takes an S, takes an A, outputs some scalar. Yeah, there's like distributional Qs, but in our case, it's going to be the expected value, so it's going to be a scalar. Yes, with me? Cool. And so we're going to use the magic of function approximation to represent Q, right? So the first thing, how do we get Q, right? Like the first thing you can get Q with is just Monte Carlo approximation, right? Which is saying that like run a bunch of trajectories, right? So run a bunch of trajectories for every single thing in the trajectory from your current policy pi theta, right? For every single thing, you take a single action, right? And so you can say every tuple gives me S and A and a sum of rewards in the future, right? You just take the sum of rewards in that trajectory. That is your sum of rewards in the future. And then I can get a mapping that goes from S and A to the sum of rewards in the future, right? Just do regression, like Monte Carlo regression. Sample a bunch from your current policy, get labels of S, A, and rewards in the future. Just do regression from S and A to the rewards in the future. Okay, so this seems great. Why shouldn't we do this? Like, why is this not a good way of getting a Q? What gives? Any thoughts? It still requires you to run the policy in the world, right? So if I want to get Q for some policy pi, I have to run that policy pi in the world, right? And I need a lot of samples. And so if I do regression from S and A to the sum of rewards, I still need to be on policy. And I'm also going to be high variance, right? So like, it's never that I'm like sampling many from the same state. I'm still sampling the whole trajectory and averaging. And so what you can show here is that it's like, it'll give you something unbiased, but you have to run it in the world and it's going to be high variance, right? So we're going to both try to avoid running things in the world and we're going to try and avoid the variance because you're still coupling things along the whole trajectory. Okay, so we want to do better. And so we said, we want to like use a little more structure in the problem to lower the variance, right? So we're going to use something about the Markov decision process to make our life easier. So we're going to do two things. We're going to try and lower the variance, and we're going to try and learn off policy, which means we're going to use past data, right? Different data that is not collected from pi. So when I say off policy, I want to like get the Q function for some pi. So I want to get Q pi theta, but I'm not going to have data from pi. I'm going to have some data from some other policy, pi beta. Yeah. And so we're going to try and estimate Q pi theta from data from pi beta. So pi beta is not the same as pi theta. Right? Yep. For the same reason that we talked about it. The Q function is also pi. Yes, the Q function is also pi. Yeah, that's something. Okay. So so the nice thing about the Q function is going to have some special structure that we can exploit, right? So this is because the system is Markovian, right? But let's try to start by looking at a Q function, right? And looking at our previous definition of a value function. So there's a Q function, there's a value function. So the Q function, remember, is the expected sum of rewards starting from S, taking an action A, and then following the policy pi. Yep. The value function is the expected sum of rewards starting at state S and just following policy pi, right? Okay, so how should I relate the value function and the Q function? Like, how is V related to Q? just look at the difference between these two things. How is V related to Q?
V is Q is when we take action, then is sum to like the value of the latest thing.
Okay, yeah. So you're saying like, I guess what you're getting at is Q is equal to some expected R plus gamma V, right? Another way, so that's one relationship you could have. The other thing you could do is you can notice that V is kind of the expected Q, right? So it's kind of like V is as if you did Q, but you sample actions from your policy, right? So you can say that V pi ST is the expectation of A sample from pi of Q pi ST AT. Right? So in general, remember that P is expected Q. Right? And so the nice thing here is that you can like directly connect V and Q. So we're going to first start by noticing some recursive structure in the value function, right? So if you look at the value function, it is the expected sum of rewards starting at time step 1 and going from there to capital T, right? Now, if you separate out the first reward from all the other rewards, right? You can say this is R and this is the remaining R's, right? And you can like separate out the expectations to say that like this one is only going to be expectation over the first step. This is going to be expectation over all the other steps. But you can write this as expectation under R plus expectation under pi of all the future R. Yeah.
But isn't the first one so conditional on ST? Like I'm curious how
It is conditioned on ST. So this expectation is going to be over like ST plus 1 on.
So it's good times like should the first term in that be R instead of a T given S?
Yeah. So this has a given ST. I just like omitted that for shorthand. Yeah, it is conditional on ST. Yeah. Okay, so you can separate out this thing is an expectation over actions sampled from pi. And this thing, the first thing is an expectation over action sampled from pi. The next thing is an expectation over next state sampled from the dynamics and future action sampled from your policy for there on after, right? So it's like, that's the first step and there's all the steps thereafter. Right? But the nice thing here is now you can notice some recursion because, I mean, what is this thing, right? This thing is basically the value function, expected value function at the next step. Right? And so the cool thing here is that you can rewrite this value function recursively as say v pi st is an expectation of the actions coming from pi and the next state coming from the dynamics of r plus v pi at the next state. So typically you'll have a discount, so you'll write this as r plus gamma v pi. And so you kind of have this nice natural recursion. This is what you'd call your Bellman update, right? So the nice thing about the Bellman update is you can write v pi at st in terms of v pi at st plus 1 and st plus 1 in terms of v pi at st plus 2, right? And so so the first thing we're going to do is notice that there's temporal structure. So like I don't have to like compute the v pi with like just samples over the whole thing. What I can do is I can compute the v pi the last step, and then I can compute the v pi the second last step by bootstrapping from the last step, and the third last step by bootstrapping from the last 2 steps, right? And so you can kind of go backwards, right? So the recursion goes backwards. And that's the key idea behind the Bellman update, which is that your value function is a recursion that goes backwards. Yeah. Okay, so given this value function, our goal is going to be to do the policy gradient update, but the policy gradient update doesn't use a value function, it uses a Q function, right? So a Q function is connected to a value function. Remind me of your name? Cool. Like Boone was saying, like you write a Q function in terms of a value function, right? So if you think of a Q function as the expectation of the Q function is taking the first action and then following the policy thereafter. You can write the Q function as the first reward plus gamma times the value at the future, right? And so you can always write Q pi as R plus gamma V in the future. Yeah. But the important thing is that the first action is according to A, not according to pi, right? And so you can, from any value function, you can construct a Q function. From any Q function, you can construct a value function. Right? And so you take the expectation of the Q function, gives you the value function, you take a one-step backup. This thing is called a one-step backup, right? You take a one-step backup of your value function, it gives you a Q function, right? And so once I do this recursive update, let's say I got my value function this way, I computed my value function, I can get a Q function, and then I can replace the like sum of rewards. Remember what I did in my policy gradient was like I had a sum of rewards, right? I will just replace that with the Q function. Yeah. And so what we've done so far is we've defined a value function, we've defined a Q function, we said value functions have recursive structure. That's going to allow us to give you the value function, and then a Q function is just a one-step backup on a value function. Okay, so what does this give us? Right, we have value functions are recursive. This is Bellman, but value functions are recursive, and so value functions follow the Bellman update. And so what you're going to do is you're going to first learn a value function. Right, so a value function says that if you have S, A, S prime tuples, you're going to construct these recursive targets, right? Basically, for any V phi S, you're going to try and regress to R plus V at the next step, right? And so you can think of this as like trying to make the left and right-hand side of this equation the same, right? You're trying to make the left-hand side, the right-hand side of this equation the same. And so you're saying that given any state action next state tuples, you're going to try and regress between the value function and the target. The target is going to be the reward plus the next value function. Yeah. And so this is going to try and make, it's going to try and make your value function obey that recursive structure. Yes. It's a good question. So in the second line over here, right? Remember that like your conditioning here is on ST plus 1, right? So like you did the first step, and then you take the rewards starting from the second step on, okay? And so you can kind of think of it as like, what is the value function at some state ST? It is the reward at ST plus the sum of rewards starting from ST plus 1. Which two lines? Second and third. So this line is like, yeah, all three lines of these are equivalent. So let's try to like work through why they're equivalent, right? So the first line is saying you want to like sum up the rewards starting from the first time step and then all the time steps in the future, right? And so let's separate out the first step from all the other time steps. Right? So you're going to say, well, the first step is just the first step. It doesn't depend on. And then you say first step plus an expectation of all the stuff in the future. Right? So all the stuff from ST plus 1 onwards. Right? And so if I consider all the stuff from ST plus 1 onwards, I'm essentially going to take the sum of rewards starting from ST plus 1 to the future. And if you look at the definition of the value function, I have it here. But the definition of the value function is basically an expectation, like the value function at some state ST plus 1 is going to be an expectation under pi theta of the sum of rewards starting at ST plus 1. Like that's the definition of the value function at ST. And so now I can take this second term and I can if I look at the second term, right, it's like saying if I started from ST plus 1 and went onwards. And so that is exactly the same as the definition of the value. That's how you get ST plus 1. So you can kind of think of this as this is all the rewards from now till the future. And that is equal to the reward now plus the sum of rewards. Good question. Okay, cool. So we want to make the left and the right-hand side of those equations the same. And so there's a little more nuance to it, but let's go with it for now. And so you're going to try and regress from, you're going to try and learn the parameters of V, which match this target, which is R plus gamma V at the next step, right? And so this is going to give me a value function. And then from any value function, I can construct a Q function, right? Just the same way that I did here. You look at the Q function, it's just R plus V in the future. Right? And so if I want to do my policy gradient update, I can do the same thing that I did in GAE. I can do the same, it's the same backup, it's all the same, right? But basically I'm going to say my Q function is R plus gamma V. And I'm going to subtract my critic. So I'm going to get R plus gamma V minus V. And I'm going to substitute that in for my sum of rewards. Right? And so I've taken my policy gradient, but I've used the magic of function approximation to say that I'm going to learn some V. But the special thing here, as compared to earlier, is we're using the like recursive structure of the problem, right? So we're saying that like V sometimes step SD is a function of V at the step SD as well. And so that's what allows you to like use some of the structure of the problem to lower variance. So this does better, like this should do better than the policy gradient because it's using function approximation to lower variance. Cool. And so you can kind of intuit like that it does this kind of thing because you're learning V and V shares information across this and this and this. Yeah. Okay, so in general, the recipe looks as follows. You start by collecting some data, you fit a value function. Right? You fit a value function, the value function does V minus R plus gamma V at the next step. You try to make those things the same. Once you get a value function, you can construct a one-step backup, which is your Q, right? And then do the policy gradient, that improves your policy. Then you sample again, and then you reconstruct your value function, and then you repeat, right? Okay, so this is a simple recipe that works. Like the challenges here are basically that the advantage is that it lowers variance, but the challenge is here that every time you have to construct that V, you have to still sample on policy, right? So every time you have to construct V, you have to like keep resampling, and that defeats the purpose of an off policy algorithm, right? So the thing we're going to try and tackle is how to deal with this on policy case, right? So just to recap what we did is we said, hey, we have this policy gradient thing. Where'd it go? We have this policy gradient thing. It's like, sorry, yeah. This policy gradient thing, we have this sum of rewards. It's like high variance. We want to get rid of it. And so we want to use function approximation to get some Q, right? The two things we're going to note is that Q is equal to R plus gamma V in the future. And then V is equal to R, like there's some expectations matter here, but essentially you can like think of V obeying a particular structure, which is this recursive structure. And then Q, V obeys a particular structure, and then Q is a one-step backup on V, right? And so you do two things. You start by learning the V, and then you do one-step backup on Q, and then you replace that for the policy gradient. So we're just policy gradient with lower variance. Okay? We're still not off policy. So the problem with this algorithm is that it's lowering variance, but it's still on policy, right? And so it's better, but it's still not as good as we could be, right? So let's cover off policy RL next time, but keep this recursion in your mind. We'll cover it on Monday. Okay, thank you.